I've been looking at sorting networks and I thought I might share what I've found out so far. So, you see stuff that looks a bit like this. It's a sorting network. What it does is it takes in a bunch of unsorted numbers. So looking here on the left-hand side, they get passed through left to right along these lines. And when it pops out the other side, if it's a valid sorting network, they're all going to be sorted. I'll try and explain what they're doing, what the idea of one is. So each of these numbers is given one of these slots. In this case, it's a size 8 sorting network. And they progress, so saying left to right. If we look at the number 6, it comes along and hits this sort of decision point. What this is an operator. I can call it a coex operator, compare and exchange. And it compares the two values, and if the upper one is smaller, they get exchanged. What it does, it means it's a min-max. So the minimum one ends at the top, the maximum one ends at the bottom. And in this case, 6 would sort of come along, it would hit here, it ended up being compared against the one down the bottom, which is 3, and so they would be swapped. And then it continues along the path, hits another decision point. I've left these dark ones to say it failed. It was not the min, it was the max. Here, it's going to end up being compared not with 8, but with whatever has progressed down to this point. So it moves down, across. Sometimes it stays as the maximum, like here. It compares with something smaller, and eventually it pops out in this position here. And so all of the numbers are moving through like that. They're doing an automatic sort with this fixed number of comparisons. Over here, this is the NumPy one. I've looked at it in the past. Here is exactly that network that was drawn. It is for sorting 8 different values, and it has a whole lot of coex operations. If you look at what this coex operation actually is, jump in here. It is a function that makes a temporary value, and then A, the first input, becomes the minimum. The other one becomes the maximum. All right. Yeah, it references this place. BERT double air sorting networks, which is this page containing a whole lot of sorting networks up to size 32. This in turn actually references my old friend Nuth. Yeah. So I'm on page 228. I mean, there are a bunch of pages. These sorting network diagrams are going to be very familiar. There's a lot of reading about properties of them, variants of sorting networks, all sorts of fun. So it looks like they've been around for quite some time. However, wherever you jump in here and look at the references, some of them talking about improvements. So this was in 2009. I mean, okay, not that recent. How about 2014? Someone's been publishing papers of optimal sorting networks. 17, 18, 19, oh my god, down to 2025. Depth 13 sorting networks for 28 channels. Nice. And so he's been good in collating all of these here. So taking a look at what it's like in Golang, this is just that exact same network again. It has been implemented with read. I just put them all into the registers. There'll be, I've got to have 8 registers around. Do mins and maxes just using the built-in function. Okay, one thing to note, if you're in a programming language where there is no built-in min-max, if you end up having a min-max operation that is doing a comparison, like if B is greater than A, then return B, whatever, stop. Okay, you don't want to be doing branching. So instead, you can just use a little tweak. Just look it up. You can do mins and max using bit twiddling. You basically work out the sign of the difference. So if one is smaller, one is larger, and use it as a mask, and you can produce the min and max. I tried both of those. It's no quicker. I think this is using the correct underlying operation. Nice. So I've compared an insertion sort, just a basic one, and a few variants of insertion sorts. This is the best one being shown here, with a sorting network just for length 8. So it's a pretty short, basic one. The numbers were always randomized. That's kind of the worst case for insertion sort, because insertion sort will finish early if it's partially sorted. However, it's only length 8, so it means that big O of n squared hasn't got a very high input, so it hasn't exploded yet. So in many ways, you're not going to get much of a better case for insertion sort. This is what we're looking at. Just understand the assumptions behind it. I mean, we're getting a speed up of close to 2 times, right? Moving from an insertion sort to the fixed operations of a sorting network. Also good. But I'm not done yet. So one thing I want to talk about now are these ideas of layers, which I'm showing here, also called the depth by Knuth. Here, if you look at these 4 comparison operations, no 2 of them are sharing any of these dots. What it means is no number is appearing in 2 of the comparisons. They're all independent. And that means that you could potentially do them all at the same time. So for this network, you can see here there are actually 6 layers. Apologies for me being in the bottom right. I know I'll be blocking a little bit, but I don't think it's anything too vital. Okay, so being able to do this potentially with 6 parallel operations could mean we could be speeding it up quite a lot over, say, 40 or so operations. How could it look using a SIMD operator? Well, I'm glad you asked. So I'll just look at the very first layer of that network. Here's what we'd have to do using some sort of AVX operations. First thing to do is to load values into memory or into a register. We need to load 8 of them, which is the standard I've been working with. You only need to do that in the first layer, and later layers you'd already have a register with these values. Perhaps that's a one-off cost. Okay, now we do some operations. First thing to do would be permute, or this is at least how I've done it, permute the array, which involves copying it as well. So it's permuted output will sit underneath, and we want to line it up to make these 4 comparisons. So for example, the one that's at index 2 is going to try and line up with index 4. That's A in this case, just some value A. I don't know if it's 1, 7, 8, 9, 15. It's going to want to line up with D. So we do a permute to, B is going to line up with D. So we do a permute to pull the D forward, right? And I've permuted all of them in a single operation to get it all lined up, at which point we can do a vectorized min and a vectorized max on these 2. So we'll end up calculating all of the mins of the pairs. In this case, an A and a C will come down here, a B and a D here. This is how vectorized works, right? It's doing pairwise. So we have now one output that's the minimum of all these pairs, and another one that's the maximum of all the pairs. And then the final thing we have to do is actually get the output for the next layer of the network as it's expected here. And so that can be done using a select. There are a few different operators that can be used. This select, paired, interleaved, get low, get high. You just have to look at them, see which ones are going to work together to give you the right kind of combination and permutation to give you the output you need. So in this case, we're just pulling down 2 of the mins and then 2 of the max, 2 of the mins, 2 of the max. So that is, I think, a select group or something like that, which can pull the same pattern from the lower order 4 and the upper order. Let's have a look what I've done in Golang. It's been implemented. This is a SIMD implementation, so you see I've got the load, I've done a permute, min max, and in this case it was select from pair grouped, right? And then the next layer, permute, min max, select from pair grouped, and set low, get high. So it's doing a little bit more of a permutation, another min max. And at that point I've actually stopped. So that's 3 layers. If we go back and take a look in this network, you'll see that the later layers are much less efficient. So these have each got 4 comparisons. This one only has 2, and then another 2, and then only 3. So you're not getting as much work done per parallel operation. So what I decided to do is just pull the values out and just do it using the same bit of min-max code from before. Okay, so how's that performance-wise? It looks a bit like this. We've already seen the insertion sort. Adding a sorting network is almost twice as fast. Adding the SIMD operations for half the layers, those first 3, is about a 10%, 15% saving. So that's not a bad start. However, I should say that I don't believe a sorting network is necessarily the optimal way of using the SIMD operations. It is assuming you have to get back to a set of 8 values, which may well not be the case. Because here, in this point, we've chosen to collapse to these 4, although in the intermediate step, we actually had 16 values. We've got a lot more memory to work with than is present in an actual sorting network. And we have even more registers we can use too. I think sorting networks is a good start. It may not be the optimal way of sorting. That might be something for the future. Anyway, that's what I've done with sorting networks so far. Thanks for listening.